calculate the voltage drop of two 12 American wire gauge conductors supplying a 16 amps load located 100 feet from the power supply, you need to consider the resistance of the conductors. When facing such a problem, especially in an exam setting, pay close attention to the information provided. If the problem does not specify whether the conductors are coated or uncoated, you need to make a reasonable assumption based on the context and general electrical practices. Coated conductors are typically used in outdoor or harsh environments where corrosion and moisture protection are essential. Uncoated conductors are more commonly used for general indoor applications. If the problem does not mention any specific environmental conditions, it is generally safer to assume that uncoated conductors are being used. Table 8, Conductor Properties, provides the resistance values for conductors. For 12 American wire gauge copper conductors, the resistance is given in ohms per 1000 feet. The question highlights the difference between uncoated 1.93 ohms per 1000 feet and coated 2.1 ohms per 1000 feet copper conductors. Since no coating is specified, use the uncoated value of 1.93 ohms per 1000 feet. First, determine the total resistance of the circuit. Because there are two conductors, one for the supply and one for the return, you need to account for the length of both conductors. The formula for total resistance is R total equals 2 times the quantity of the resistance per 1000 feet times the length of the run-in feet divided by 1000. Plugging in the values, R total equals 2 times the quantity of 1.93 ohms per 1000 feet times 100 feet divided by 1000. This simplifies to R total equals 2 times the quantity of 1.93 ohms per 1000 feet times 0.1. Multiplying these values, R total equals 0.386 ohms. Next, use Ohm's law to calculate the voltage drop. Ohm's law states that voltage equals current times resistance, or volts equals amps times ohms. In this case, the current is 16 amps and the total resistance is 0.386 ohms. Therefore, the voltage drop, volts drop, equals 16 amps times 0.386 ohms, which equals 6.176 volts. Rounding to 2 decimal places, the voltage drop is approximately 6.18 volts. Therefore, the voltage drop of two 12 American wire gauge conductors supplying a 16 amps load located 100 feet from the power supply is approximately 6.18 volts, assuming uncoated copper conductors. It's important to understand the problem's context and industry standards to make reasonable assumptions when information is not explicitly provided. In real-world installations, several factors influence conductor selection and voltage drop calculations. Firstly, conductor material. Copper and aluminum are the most common conductor materials, each with different resistance properties. Copper has lower resistance than aluminum, so it experiences less voltage drop for the same current and conductor size. Aluminum conductors are lighter and less expensive, but they require larger sizes to carry the same current as copper conductors with an equivalent voltage drop. Secondly, conductor temperature. The resistance of a conductor increases with temperature. Higher temperatures lead to increased resistance and therefore increased voltage drop. The National Electrical Code, or NEC, specifies temperature ratings for conductors and provides ampacity correction factors for different temperature environments. Thirdly, conduit type and fill. The type of conduit and the number of conductors within the conduit affect the heat dissipation and thus the conductor temperature. Overcrowded conduits can lead to higher conductor temperatures and increased voltage drop. The NEC specifies the maximum allowable conduit fill to prevent overheating. Fourthly, load type. The type of load, such as resistive, inductive, or capacitive, affects the current drawn from the power source. Inductive loads, like motors, can cause voltage drops due to their reactive impedance. Capacitive loads can cause voltage rise under certain conditions. Fifthly, allowable voltage drop. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Exceeding these limits can cause equipment malfunction, overheating, and reduced efficiency. Sixthly, conductor insulation. The insulation type affects the conductor's temperature rating and its ability to withstand environmental conditions. Common insulation types include THHN, THWN, and XHHW, each with different temperature and moisture resistance properties. Seventhly, dilating factors. The NEC requires dilating conductor ampacity when multiple conductors are bundled together or when conductors are exposed to high ambient temperatures. Dilating reduces the allowable current to prevent overheating and voltage drop. Eighthly, installation method. The way conductors are installed, such as in free air, in conduit, or buried underground, affects their ability to dissipate heat. Conductors installed in free air have better heat dissipation than those installed in enclosed conduits. Ninthly, voltage drop calculation software. Several software tools are available to simplify voltage drop calculations. These tools take into account various factors such as conductor size, material, length, current, and installation method to provide accurate voltage drop estimates. Tenthly, the use of appropriately sized conductors. Selecting the correct conductor size is crucial for minimizing voltage drop. The NEC provides tables and guidelines for determining the appropriate conductor size based on the load current, conductor length, and allowable voltage drop. Here is a more detailed breakdown of how these factors influence voltage drop calculations. Let's delve deeper into conductor material. Copper conductors offer excellent conductivity, reducing voltage drop and improving energy efficiency. Their high cost is often justified by their superior performance and longevity, especially in critical applications. Aluminum conductors, while less conductive, provide a cost-effective alternative for large installations where the increased conductor size is not a significant constraint. Now let's consider conductor temperature. Higher operating temperatures increase the resistance of conductors, leading to greater voltage drop and energy losses. The NEC specifies maximum operating temperatures for different insulation types, ensuring safe and efficient operation. Proper ventilation and adherence to ampacity dilating factors help maintain conductors within their safe operating temperature range. Next, we have conduit type and fill. The type of conduit, such as metal or PVC, influences heat dissipation from conductors. Metal conduits provide better heat dissipation than PVC conduits, reducing conductor temperature and voltage drop. Overfilling conduits restricts airflow, increasing conductor temperature and potentially causing insulation damage. The NEC specifies maximum conduit fill percentages to ensure adequate ventilation. Considering the load type, resistive loads like heaters and incandescent lamps draw current that is in phase with the voltage, resulting in a straightforward voltage drop calculation. Inductive loads, such as motors and transformers, draw reactive current that lags the voltage, increasing the overall impedance and voltage drop. Capacitive loads, like capacitors and electronic ballasts, draw reactive current that leads the voltage, which can sometimes compensate for inductive voltage drop, but may also cause voltage rise. The allowable voltage drop is a critical factor in electrical system design, ensuring proper equipment operation and minimizing energy losses. The NEC recommends limiting voltage drop to 3% for branch circuits, which supply lighting and receptacle outlets, and 5% for feeders, which supply power to branch circuits. Exceeding these limits can cause dimming of lights, reduce motor torque, and overheating of equipment. Now let's consider conductor insulation. The insulation type determines the conductor's ability to withstand heat, moisture, and chemical exposure. Common insulation types include THHN, THWN, XHHW, and their variations. THHN insulation is heat resistant and suitable for dry locations. THWN insulation is heat and water resistant and suitable for wet locations. XHHW insulation is cross-linked polyethylene and is suitable for both wet and dry locations with high temperature ratings. Ampacity dilating factors play a crucial role in preventing conductor overheating when multiple conductors are bundled together or exposed to high ambient temperatures. The NEC provides dilating tables that specify the percentage reduction in ampacity based on the number of conductors in a conduit or cable. Ignoring dirtying factors can lead to excessive conductor temperatures, insulation degradation, and potential fire hazards. The installation method significantly affects conductor heat dissipation. Conductors installed in free air have better heat dissipation than those installed in enclosed conduits or buried underground. The NEC provides different ampacity tables for different installation methods, reflecting the impact of heat dissipation on conductor temperature. Considering voltage drop calculation software, these programs simplify complex calculations by automating the process and accounting for various factors such as conductor size, material, length, current, and installation method. These tools help electrical engineers and contractors design efficient and compliant electrical systems. Finally, the appropriate sizing of conductors is essential for minimizing voltage drop and ensuring efficient power delivery. The NEC provides tables and guidelines for determining the minimum conductor size based on the load current, conductor length, and allowable voltage drop. Increasing the conductor size reduces resistance and voltage drop, improving system performance and reliability. In summary, calculating voltage drop involves considering several factors, including conductor material, temperature, conduit type, load type, allowable voltage drop, insulation, dirtying, and installation method. By understanding these factors and using appropriate calculation methods and software, electrical professionals can design safe, efficient, and reliable electrical systems that meet the requirements of the NEC and ensure optimal performance of connected equipment. These principles apply not only to exam scenarios but also to real-world electrical installations, ensuring that electrical systems are designed and installed safely and efficiently. By understanding these concepts, one can approach electrical problems with confidence and accuracy.